Hi, my name is Intan Azina. I will talk about simulation in comparison to SIMULINK. As instructed in the lab sheet, we must first compile this block model. By clicking the library browser button, we'll launch it. All of our models and blocks are kept in the library browser. All we have to do is use the library browser search function to look up the type of block model we require. Such as if I want to search gain, I type the gain on the search library browser. We can get the gain. After we know how to search the model in library browser, we must set up the step, sum, gain, PI controller, plan, and scope. I would like to explain the function of these 6 models. The first one is step. The function of the step is to provide a step between two definable levels at a specific time. The block's output is the initial value parameters value if the simulation time is smaller than the step time parameters value. The output is the parameter value for the final value when the simulation time is greater than or equal to the step time. Next, the sum block. Adds or subtract the values it receives. The block for add, subtract, sum of element, and sum are interchangeable. The input to the block can be scalar, vector, or metric. Additionally, it has the ability to collapse a signal's component and sum them. After that, for the gain, a constant value is added to the input by the gain block. Each of the input and gain variable may be a scalar, vector, or metric. The gain parameter, we can define the gain value. Element-wise or metric multiplication can be specified using the multiplication option. In addition, the PI controller is a feedback control loop that determines an error signal by comparing the output of the systems in the case, the power being drawn from the battery and the set point. The plant with complex characteristics such as long time delays, higher order dynamics, or strong interaction are particularly well suited for model predictive control. And lastly, for the scope offers a variety of ways to present simulation data and record it for subsequent examinations. The different data display and data collection techniques are represented by symbol on our block diagram. Let's start our simulation in part B-A. We must modify the transfer function of the plan in the final exercise with a value that will be decided by our lab instructor. First step is to set the gain value by clicking on the gain block and changing the value to 5. After that, we must set up our plan in accordance with the provided example while maintaining our own value. We employ 41 over s power of 2 plus 2s plus 41 for our ideas. Next, double-click on the right mouse button and click and select Model Configuration Parameters to set the stop time Our elapsed stop time is 15. We must click on the scope in order to get the output signal. Then, we click on the Run button. After we run our simulation, we must click on the scope in order to get the output signal. You can see this is the output signal. The rising time is 69.668 milliseconds and the overshoot is 92.383%, while the settling time has not occurred. When the setting time does not occur, it indicates that the output for this graph is not stable. Then we will go on our simulation in part B. We use the identical approach as in part BA, but this time we only need to change the K gain values. There are 4 types of the value that can be based on the query. For example, 0, K max over 4, K max over 2, 3 K max over 4. As we know, our K max value is 5, so we can receive different values of K. We must compute it. The first K value is 0, the second is 1.25, the third is 2.5, and the last one is 3.75. Then after we know the K value, we must do some simulation. Then after we know the K value, we must do the simulation described in part BA. The stop time is kept at 15. The run button is then pushed and the scope is selected. The output signal will then be obtained. Finally, we can see our result for the rise time, TR, overshoot, MP, and setting time, TS, for the 4 K values is obtained. I will show you the result for the 4 K value is. The first one, if the K value is 0, this is the graph. When the K value is 0, the rise time is nothing. The overshoot is nothing. And the setting time is nothing. The graph shows it was an unstable graph. Next, when the K values is 1.25, this is the graph for the K gain 1.25. The rise time is 180.943 milliseconds. The overshoot is 18.771%, and the setting time is nothing. Then, when the K gain is 2.5, this is the graph when the K gain is 2.5. The rise time is 1 to 6.526 milliseconds. The overshoot is 3.112%, and the setting time is also nothing. And lastly, when the K gain is 3.75, this is the graph when the K gain is 3.75. The rise time is 1.609 milliseconds. The overshoot is 63.194, and the setting time is nothing. I came to the conclusion that setting time is affected by the damping ratio and natural frequency. All of our results regarding the statement time does not occur. It may be assumed that rising time decrease, the percentage of a should increase, and the setting time increase. When the setting time does not occur, it is because the gain has increased to such an amount that some systems can become unstable. Thank you.